So how does it start? I just start
Yeah.
the lecture.
Yeah.
Okay. So hello everyone. So my name is Ramakrishnan Natesan. I'm a postdoctoral fellow in the Department of Bioengineering at University of Pennsylvania. So today's lecture, I'm going to take a very simple numerical method and show you how to use Python programming and all the inbuilt things in Python in order to solve those problems. This is just a very basic introduction to this particular programming thing in Python, but you can always build up on based on this lecture. So I just showed you where the resources are. You just need to go there and just follow what exactly I did. So taking you through what I'm going to do today. So the only one problem, so though I have mentioned multiple problems in the abstract, namely the numerical methods as a solution for solving a system of linear equations, and I also talked about numerical integration. Then as a course, when I prepared this lecture, I found that it's kind of way too high to finish in an hour or so. So which means I strict myself to only to the solving the numerical, solving a system of linear equations. So that's the main focus, that's the main numerical method to be focusing on today. And addition to that, I'll be showing you some handwritten code of using Python for the same thing. For all the methods I'm discussing, I'll be presenting the codes which was written by me. And finally, those codes are there in the two scripts which I provided with this particular lecture. So the first script is called the Gauss Elimination.py. The second one is called decomposition.py. So these two codes should be available online, and you can just download it and play around with however you like. And finally, before I close, there will be an introduction to the NumPy and SciPy modules. This is the numerical Python and the scientific Python modules in Python. And I will show you exactly how to solve those previous problems, these two problems which I already mentioned here, the Gauss elimination and LU decomposition, which was earlier solved using a handwritten code. Now we'll be using one of these modules in NumPy and SciPy in order to solve those problems. So I'm going to, so this is the main layout of today's lecture. So can everybody see the slides? I kind of see it. Yeah. Okay. Is it done? Yeah. Okay. Is it visible, Joe?
Yeah, it is. Yeah.
Yeah. So before I go into all these details of programming and numerical methods, now the main question is, why should people use Python? Why is it so? What makes it a so powerful tool so that everybody talks about Python? So the first thing is, Python can be used even from a single terminal. For example, you can just take a small. It kind of stands alone, unless and otherwise like C programming or Fortran programming or Java programming. You take any of those programming languages, you need a specific setup. For example, you need to have an editor, you have to write a code, then you have to go run the code, and you have to do a lot of this, follow the same setup things, which may be too much for very simple jobs. So, but Python kind of overcomes all those hurdles, and using Python, you can just do programming just like opening a window. You can just type in something and it will give you the results. So, which makes it a very powerful tool. And it's also, though it's very simple in some sense, you can always write full-fledged codes. For example, you can write the whole object-oriented programming style of coding in Python. And if you don't believe me, you can go and find out all the type of programs which have come out using Python. There have been a lot of softwares which are used for 3D analysis, mostly like ParaView, like Mayavi. There are a lot of programs which are used for the purposes of fluid dynamics. These codes are fully written in Python. So these are really huge programs, and they are all written in Python. So they are all written using this particular style. And finally, it's a multi-platform language, in the sense that though you have multiple operating systems, for example, you have Windows, you have Linux, you have Mac, you have all these different operating systems, and a code written in any of these platforms works in the other. For example, if your professor is writing his or her code only on Linux machines, and if he passes on this code and you want to run it on a Windows or a Mac, you are free to do it. There is no change you need to do. It just basically it's portable from across the multiple platforms. So that's another main advantage of Linux, of Python. And finally, it is widely adopted by the scientific community. A lot of people are now started using Python, so that you have a lot of information, lot of knowledge which is coming out from all these codes which are written by people. For example, there is this very good bioinformatics tool in Python, which is kind of can be used for doing any of this bioinformatic problems, which basically which are all available for free. So the final thing, which is the free, that's what makes it more appealing, in the sense that you do not pay you do not pay anything from your pocket to work on this very beautiful language. So this is my view about why people should use Python. Okay, so now going back. So as I mentioned in my abstract, I will just give the outline of the method I'm going to use, so that you exactly know what is running in the code, and from there I will take you to the part of the programming. So now I'm going to talk about a system of linear algebraic equations. It can be in any number of variables. For example, let's take only two variables here. So you can see this particular equations on the right. There are two equations, 2x and 3y equals 5, and 5x plus 7y equals 12. These are the two equations I have. Now the question is, I know these equations, but I have two unknowns I have to find. So I have to solve them simultaneously. That is, if I find out what is x, I can find out what my y is. So in a general description, this whole system of equations can be written in this particular format. This is for two variables, while this equation is for n variables. Now if you have n variables, you know from your basic math excuse me, you know from your basic mathematics that if you have n variables, you should have at least n equations to solve this equation uniquely. So here I had two unknowns, so I have two equations, and here I have x1, x2, x3 up to xn, which means I have n unknowns, which means I will have n equations like this. So this is the first equation, and this is the nth equation. So this is the basic problem we are going to solve. We are given n equations. I want to find out what are the solutions for this particular problem. You can ask me where this problem comes in. This problem virtually comes everywhere. Every application you do, every engineering problem you do, every physics problem you do, this particular system of equations always comes in. You need to solve multiple equations at the same time in order to get a solution. So instead of writing in this clumsy format here, it can be written in a very compact format like this. All the A's, all the values of A, for example, A11, A12, A13, A21, 22, 23, 2n, all these things can be put together right to be into a matrix. So this particular script says that this particular object is a matrix. So A is a matrix, and the x1, x2, xn is a vector. It's a kind of a one-dimensional matrix, and the constants, which are b1, b2 up to bn, they are also another matrix. So you have a matrix which is multiplying a vector, which will give you a vector. And you know from your simple matrix analysis that if this is n by n and this is n by 1, and then this finally is going to be n by 1. Okay, this is the normal thing we know from matrix analysis. So this is the form of equation we have. Now the question is, how do we solve this problem? So this problem can be solved very easily. We multiply this side, the left side of both the A and B by A inverse. So let's say A inverse XS. A is the matrix. I'm going to find out what is A inverse is. And if I multiply the left side of both A and B by A inverse, then A inverse A becomes a unit matrix. It becomes 1. And 1 into X is going to give you X. While the left hand side becomes A inverse B. So you have a solution. So you finally found the solution, which is X is A inverse B. That is, you can get the whole solution just by a matrix multiplication. So this is basically the framework in which we are working in. Now, there are certain conditions that should be satisfied by this matrix A for it to be solvable. For example, it should have a non-zero determinant, and this particular system works only when the equations are linearly independent. So these conditions should be satisfied. I'm not going to go into these details because that's not the focus of this particular class, but I should give you a warning that these particular things are already taken care of in most of these programs where you use to solve these particular problems. Now, to appreciate this fact, why this problem should be there. Now let's take two equations. The first equation, the first is in two dimensions. I'm talking about x and y. So the first equation has a line like that, and the second equation has another line like that. And all we are trying to seek is find out the point at which the line A and line B intersects. So now in this particular case, you can find that this particular system has a determinant which is non-zero, because if you look at the space which is spanned by these two vectors, these vectors have a non-zero area. Okay, so this is vector A, this is vector B, and the area is basically A cross B, right? So if I do a cross B, this particular vector is going to give you a finite area. So that area is nothing but it's nothing but the matrices. It basically decides whether the inverse exists or not. So while in this particular equation, since A and B are the same equations, you will find that the cross product between A and B is going to be 0, which means the matrix doesn't have the norm of the system is 0. So that doesn't exist. So the matrix doesn't have an inverse. So the matrix doesn't have an inverse. So this particular system is called ill-behaved. So to appreciate this further, now let's go and use our normal well-known method for solving numerical problems. So one is very frequently used, this is everywhere, it's in Matlab. So in Matlab, if I give a matrix A which has this particular form, for example 2, 3, 5, 7, and if I ask what is the solution for this, okay, so the solution can be determined by typing this following code into Matlab. You define matrix A, define matrix B, like how I did, and ask the question X is A / B, and that should give you what exactly the solution is. So if the matrix is well defined, A is well defined, then it will give you the exact solution. On the other hand, if I type in a matrix which doesn't have any, which is basically ill-behaved, then it will automatically say that the matrix is singular. So it automatically takes care of. So there is a particular set of problems that can be tackled. There is a limitation on the set of problems that can be tackled. So this is basically the well-known numerical method. So here I'm warning you just to make sure that you know what exactly you're doing, because later I'm going to introduce you to something like a black box where you put in something, you're going to get some results, but you should be making sure that you're putting in the right numbers to get the right results outside. And this numerical methods has been known for a very, very long time. And most of you must have heard about this package called LAPACK, which is the linear algebra pack. John, is somebody raised the hand or something? I got some feedback from.
Okay, probably not.
Okay, fine, that's great. So this LAPACK is a library which basically does many numerical methods. If you go to your libraries, you'll find this book called Numerical Recipes in Fortran and C. Okay, this is basically the whole development of this package called LAPACK. And this has been written in most languages, C, Fortran, Java, everything has this LAPACK. And now currently it also comes as a part of the system library. The system also has the operating system itself has a library, and it comes as a part of the library. So in case we want to use the LAPACK, you can just call the system library directly. So this is my introduction to this particular part. Now, what is the method of solutions? How do we really get solutions for such problems? So if you refer to the book I have suggested in my abstract, they list two methods. One is called the direct method, another is called the iterative method. So we will be focusing more on the direct method because it's easy to understand and easy to execute. While iterative methods are nothing much than just you start with a guess, then you keep iterating till you get the right answer. Okay, so there is no trick involved here, it's just cumbersome. It's a lot of programming to do. So we will not focus on the iterative methods in this particular lecture. In this particular lecture, we will be talking about the three methods, basically the Gauss elimination method, the LU decomposition method, and the Gauss-Jordan elimination. I have not talked about the Gauss-Jordan elimination in the code, but I can suggest that I'm going to give this as a homework for you people following the two methods I had done before. So let me give a small introduction to all the notations here. So A is the matrix which I already introduced to you here. So this matrix contains the coefficients of the equation. That's what matrix A is. And X is basically the unknowns, the n unknowns you have in your system of equations. And B is the coefficients, the constants. So if I go back here, all those B's put together is the B I shown in this particular equation. This is what B is. Now, this particular table tells you that what this method tries to do. What this method tries to do is takes this matrix Ax comma B, does some transformation to get another matrix which is Ux equal to C, where U is nothing but a matrix which has all the lower diagonal elements to be 0. So this is called the upper diagonal matrix, which means the elements only in the top, it's in the diagonal and above the diagonal are non-zero. So that's what is the U matrix U. And similarly, you have matrix L, in which instead of the lower diagonal being 0 earlier in U, here the upper diagonal is 0, which means you have only non-zero values in this particular region, just below the basically in the lower triangle. So this is basically the very simple framework I'm going to stick to for the next 20 slides or so. So going back here, okay, so what is this method for Gauss eliminations? So Gauss elimination, I told you, I'm going to do a series of transformation to convert a matrix which has this particular form. For example, for this particular system, I have chosen an example which is 4 minus 2 1 minus 2 4 minus 2 1 minus 2 4. So if you read it, the equation should read like 4x1 minus 2x2 plus x3 equal to 11. 2x1 plus 4x2 minus 2x3 equal to minus 16. So this is the set of equations. Now I'm going to convert these equations into a matrix form first. So in the matrix form, the 4 minus 2 1, they form the first row. Minus 2 4 minus 2, they form the second row. And 1 minus 2 4, they form the third row. And this particular line denotes that I'm going to do this operations simultaneously. And 11 minus 16 7, that constitutes the region A. Sorry, this constitutes B. So how do I write on the thing, Joe?
Yeah, so you click on the bottom right hand side.
Okay.
Of the, yeah, and then choose the.
Okay. Hold on just a second. Yeah, I got it. So this particular one is A, and this guy is our earlier B. So what I have done here is, I want to get rid of, so I'm going to do, so this Gauss elimination has two phases. First phase is called the elimination phase, where you take this matrix and make some elements of it 0 depending on your need. Suppose in this particular example, I'm going to convert the matrix into a matrix which has only the upper diagonal elements to be non-zero. So for that, what I do is, there is this particular method called using the pivot equations to modify, to transform the rows and columns of a matrix. You will all know that when you uniformly transform the rows and columns of a matrix, it doesn't changes the property of the matrix itself. So in this example, I need to get rid of the columns in the lower part. I don't want this number, I don't want this number. I want to take them off. So what I do is I devise a method where I multiply row 1, I add up row 1 to row 3 with a multiplicative factor. So in this particular case, what I did is I took row 3 and said row 3 is row 3 plus row 1 divided by 4. So pardon me, this is row 3 minus, this is minus row 1 minus 4. So this should be a minus. This is R3 equals R3 minus R1 by 4. So if I do that, R1 divided by 4 will give you 1 minus 0.5 and my 0.25. So if I subtract both of them, then you will end up with 0 and you will have 1 minus 1.5 and 3.75. And I had to do the same operations on B also, which means I had to do 17 minus 11 by 4. That's the operation I'm supposed to do at that particular place. So this is one operation which gives me the new row 3. The same way I have to do an operation for row 2 because I need to get rid of this element in row 2. This minus 2 should go off. So the simplest way is divide row 1 by 2 and then add it to row 2. So R2 is R2 plus R1 by 2. So I do the same operation. So now I got rid of the first and the first column in rows 2 and 3. So those two elements became 0. But still this matrix is not a upper diagonal matrix. So what I should do is I have to perform another operation where I get rid of this minus 1.5. So how do I get rid of this minus 1.5? It's very simple. I can just take row 3 and add it with row 2 divided by 2. So 3, you have 3 by 2 is 1.5. I add it up here, you will get 0. So that particular operation leaves me with this particular system. So instead of having this whole set of equation, now your equation reads 3x3 equals 9. I'll start from the bottom because these two elements are 0. So the first reads 3x3 equal to 0. That's what I have here. 3x3 equal to 9. And that gives me x3 equal to 3. So earlier I had 3 unknowns. Now I solved 1. So I got the value of x3. So once I get the value of x3, I can go to the next previous equation where I can say 3x2 minus 1.5x3 is minus 10.5. That's what I have in this particular thing. But since I know the value of x3 equal to 3, I substitute it inside. Then I have 3x2 minus 4.5 equals minus 10.5. And finally you will get 3x2 equals minus 6. So that will give you a solution which is x2 equals minus 2. And since you know x2 and x3, you can do the same trick here and ask what is x1. So this method where after you convert the matrix into a diagonal form, you're going to substitute this, or you're going to solve this particular thing. So this particular phase of this solution is called the substitution phase, where you use the converted matrix to get the solutions. And depending upon what type of elimination we are doing, we have to use two methods. Let me go here. Okay. So this is the general framework for the elimination. So this elimination can be done in such a way that you either get rid of all the elements above the diagonal or all the elements which are below the diagonal. So if you get rid of all the elements above the diagonal, you call it lower diagonal matrix, and that is which is our L in our previous representation. And if you get rid of all the elements which are below the diagonal, then you have a upper diagonal matrix which is U. So if you look through this is the operation I had earlier done. I said row 1 is row 1 minus some factor times row 3 or row 2, whatever it is. So the row which is being used as the object is called as the pivot row. That's the row which is going to be multiplied and added to something else. So in this particular code, I have given you a simple numerical technique where if you pass two matrices. For example, I have to pass two matrices. Here you have matrix A. This is matrix A, and this is matrix B. So you have these two matrices. So you have to pass them simultaneously into the code. So I'm passing these things to A and B to a function which is called convert to upper diagonal. And what this does is exactly the thing I outlined here. All the operations which I had been doing here, this is programmed to do using the first row. It always uses the first row to do all these calculations. I think I will not get into the code, John. Probably I'll just leave them to look at it.
Yeah.
Right?
Yeah, that's yeah.
So this is basically the method for doing a conversion to upper or lower diagonal matrices. Now I have to bring to your notice that the substitution need not always start with x3. So in this particular example I used, where I convert the matrix into a upper diagonal matrix, I did something called the backward substitution, where I start from x3 and then go up. While if I convert the matrix into a lower diagonal form, then I will not do a substitution which is in this type. I will start from x1 and then I'll find x2 and then I'll find x3. So the sequences, whether you find x3 first or x1 first, tells you what type of substitution you should be doing. You should be either be doing a backward substitution, and backward substitution is basically associated with converting to upper diagonal matrices, while forward substitution is done when you are when you are converting the matrix to your lower diagonal matrix. And the technique so this whole thing which I showed here, where I took x3, found the solution, then substituted here inside, and substituted x1 and x2 to get x2 and x3 to get x1. All these things can be written in a very compact form like this, where this is xk. So now let's look at this equation very carefully. Now let's say we are doing x3 in our previous example. So you can see that x3 is nothing but b3 and minus the summation goes from 4 to n, but you find that your n maximum is 3. So 4 to 3, this summation will not exist because I goes from 4 to 3. So this particular summation is basically doesn't sum over. So you are left with this element to be 0. This element is 0. So finally you have x3 is b3 divided by a33. Is that the solution we have here? Now let's go back to this equation, the final equation. So we said x3 is b3, which is 9, divided by a33, which is 3. So finally it gives you the solution, which is 3 here. And you can work this out by yourself for x2. For x2 it should be x2 is b2 minus a23 x2, sorry, a23 x3 divided by a22. That's the final relation you have. So this compact equation can be written in a very compact form like this. So if I give you the matrix B and if I give you the matrix A, which is MA and MB here, I can find out xk just using one line of the code. Just one line of the program is enough to determine this. So this particular thing runs a loop, and the loop goes from say 3 to 0, 3 to 1. The same way you can also do the forward substitution. So the forward substitution method, instead of finding x3 first, you're going to find out x1 first, and you can work out you'll get the same thing again. And here, unknowingly, before I introduced numpy, I have used something called the numpy dot, which is a function to do dot products. So this whole thing is nothing but a dot product. It's basically a thing, something like a dot b. So I have used the numpy dot product. So I just mentioned it here because you should be aware what this is. So I'm going to I didn't want to write a code which is basically doing the dot product by itself. Okay, so now coming to this code, I'm not really sure. I was not really sure how much of programming experience you have with Python. So what I did was I just try to lay out a code where I use the object-oriented programming style to kind of solve this particular problem. So first I'm going to present to you this code called Gauss Elimination.py, which is the Python code for doing the Gauss elimination. So now I am defining the following objects. So these are all very generic things. It's not like, we are not writing the code for just one given matrix. So we are writing the code general enough that it can handle any matrix at any matrices of any dimensions. So we have two objects for the elimination phase. So I told you Gauss elimination has two modules. The first part is the elimination phase, where you convert the matrix into the form you like, and the second part is the phase where you do the substitution. So for the elimination phase, I have two methods here. The first method is called convert to upper diagonal. So which means I have two matrices MA and MB, which is passed to this function. And what the code does is, first since it's generic, it's a very generic code. First it determines what is the dimensions of this array. That is, we are asking the question, are we solving a matrix which is of size 3, a 3 by 3, or is it a size n by n? So that is decided at runtime when the matrix is passed. For example, you can use the same code to pass matrices of 4 by 4, 5 by 5, 6 by 6, any size you like. So the only thing it does is it determines the size during the runtime at this particular point, and then it executes the algorithm which I presented in the previous slides. Exactly, this algorithm is basically executed there. So this is called an object. This particular thing is called an object for converting to upper diagonal. And similarly, I had defined another object which converts it to the lower diagonal. It also follows exactly the same way, except for some variables, ways in which this loop is written. And again, there are other objects for the substitution phase. For the substitution, you have forward substitution, you have backward substitution. So now I first define the backward substitution. So the backward substitution also works in the same way. You determine the length. Now you see that I purposefully wrote two different ways to determine the length of the particular matrix. Suppose if we give you a particular matrix, there should be two ways of writing what is the length of this matrix. So one is just use the shape operation in NumPy. Other one is use the well-defined length function in Python. This is the whole Python thing. So now I execute the algorithm here at this point. This is the place where you compute all the solutions and you pass the solution back. So now let's go a step ahead and see how this whole thing is now integrated into a single code. So this is the main part of the Python code which I gave you. So this is similar to our main function in any of the programming languages you have. So what this program does is, I have two matrices A and B in forms of files. Rather, I feel it nicer to put it into a file rather than asking the user to keep entering, because they can make a lot of mistakes when they enter, rather than entering into a file. When you enter into a file, you can easily see what's there. So what this code does is, it first reads the matrices A and B. A and B are read, so they are read into variables called A original and B original. And it does some very basic checks. For example, one check I have put in here is, I have put in a check whether the dimensions of A and B matches with each other. For example, if you have a 3 by 3, if you have A as 3 by 3, it's important that B should be 3 by something. It should be 3 by 3 or 3 by 4 or 3 by 5, whatever it is. So if those dimensions do not match, if the first dimensions do not match, then this code is not going to run. So it's going to print some error message saying that array dimensions do not match and restart with the correct array, and the system is going to exit. But if you have everything right, then the first thing it does is, it's going to use one of these methods I defined previously. I had defined all the methods here. So first I'm going to use the method to convert the matrix into lower diagonal matrix. So I copy the original matrix to A and B. Remember, in most of the programming languages, if you pass an array and if you do any modifications to the array, sometimes the array may be overwritten. So I don't want to do that because I want to use the A original and B original throughout all the different steps I'm doing. So what I do is I make a copy of A original and B original to A and B. So this is a compact way of writing A equals A original and B equals B original. So I write it in one line, which is it says that A comma B, which means it should read it like this. So this comma is the separator. So it will find out the object before the comma and say A is connected to this guy and B is connected to this guy. So I have the array copied, and once I have the array copied, I'm going to call this object, which is convert to upper diagonal. Okay, sorry. I'm going to convert to upper diagonal. So once I convert to upper diagonal, I'm passing the variables A and B. Now, since it's changing everything, now after the conversion, you will find that matrix A has a different form. So let me go and show you the results when I run this code. So this is a code I ran from my terminal. So here you find that I typed in Python Gauss Elimination.py with all the matrix. This is the matrix files I used. The matrix A.dat and matrix B.dat. These are the original values which you saw earlier in the program there, in the introduction to this code. So matrix A is stored as a data file and matrix B is also stored as a data file. So now I call Gauss elimination. It says Gauss elimination by converting A to an upper diagonal form. So once you do that, you'll find that A has now changed. A was here. It had a full form like this, but now it lost all its elements below the diagonal. So it has it has the form of the upper diagonal. So this was done in a very simple way. I just called A comma B using the function convert to upper diagonal. And now finally I go here. So these are all the different steps. This is all just for the details. I just put in all these print commands. So now it says printing determining solution by backward substitution, because you know that when you convert it to an upper diagonal form, the first thing you need to find out is x3 rather than x1. So you have to use the method of backward substitution. So what does this is, it says x is backward substitution A comma B. So it takes the converted values of A and B and then passes it to the function backward substitution to get the solution x. And finally you'll find that the solution is 1, minus 2 and 3. So this is the solution using conversion to upper diagonal form. Okay, so this is just a piece of the code. Since I cannot paste the whole code into the presentation, I'm just pasting it piece by piece. So following this particular thing, I'm having another piece which says solution by substitution to obtain lower diagonal matrix. So now I'm going to have a lower diagonal matrix. So I do the same trick. I copy A and B from the original array, because you remember when I did this conversion to upper diagonal A and B, the A and B were changed because the whole array operated on whatever you passed. So it's going to be changed. So if you pass the A and B you got without copying, then you're going to get wrong results. So what I do again here is I start fresh by saying A and B is now again A original and B original. And remember, this is the beauty of Python. Here I'm just saying A equals A original without even thinking that it's a matrix. In normal C and C++ programming, if you want to say copy matrix A to matrix B, suppose we want to copy a matrix to another matrix, you remember we had to run over all the loops. For example, you have to say I equals 1 to 3, J equals 1 to 3, then you have to say Bij is Aij. You have to do a lot of coding business there. But Python basically simplifies all these things to you with just one command which says A equal to A original and B equal to B original, which implies that you have to copy the whole matrix into another matrix which is A. So again I call convert to lower diagonal of A comma B, and again it prints the number, and then again now it determines solution by sorry, this should be forward substitution. This is backward, so this should be forward substitution. So this method is forward substitution. So you have to read this as print determining solution by forward substitution. And you have x equals forward substitution of a comma b. And finally, if you go here, they all run together. So you start the code. So first it does the conversion to upper diagonal form and then does the backward substitution to give you a solution which is 1, minus 2 and 3. Similarly, it converts the matrix to a lower diagonal form and again does a substitution. Now it's a forward substitution to give you the same solution. So what I have shown you here is I have written the codes myself and I just showed you that using either ways we can get the same solution. So now let me ask you, do you want to go through all this trouble in order to solve this problem? So now if you ask me, if you're a learner S, if you want to learn numerical methods for your first time and you want to really understand what's happening, yes. But if you are well versed with numerical Python or you're well versed with numerical methods, and if you think, if you're a kind of a researcher who really want to use these things in your day-to-day applications, then my answer would be no. I don't want to use. I don't want to write my this huge lines of code every time. So for that, what I suggest is people use the Python libraries. So this Python libraries basically comes in two things. One is called NumPy, which is the numerical Python, and another is called the SciPy, which is the scientific Python. And you should be noticing that SciPy contains everything in NumPy. So basically, NumPy is a subset of SciPy. SciPy has even more functionality than NumPy. So this is what if you go to the web page of NumPy and SciPy, this is basically the description they gave about this particular packages. So I have just pasted some screenshots for you only with regard to this linear algebra package. So you have this package called NumPy, and inside NumPy, so NumPy itself is a huge package, and inside that there is another package called the linear algebra package, which can do a lot of things which are listed out here. So you can see that it does the dot product, it does the inner product, outer product, tensor products. Okay, it can does the cross product. It can do eigenvalues, eigenvectors. It can do a lot of things with regard to matrices. So now I'm going to use one of these modules in NumPy and SciPy to solve this problem again, to solve the system of the equations which I had before. Okay, so I'm going to skip this again. So this particular slide tells you again all the objects which are available. So this objects basically means this is similar to the def function we had. So in our original code we wrote, we defined all these objects. So these objects basically, so these are the same things in which have been returned and optimized and checked and did everything. So these things are very standard objects which you can call without even writing a single line of code. Okay, so let me take this off. Okay, so now the whole big code, you remember we wrote something like some 30-40 lines of code to solve the problem. Now instead of that, I start at this particular point by reading the matrices here. I read this matrices and I don't do any of these calculations, but instead directly I go and I just do this. So Python has something called the the style of importing, which means everything is in separate boxes. So NumPy is a separate box, SciPy is a separate box, Python is a separate box. So suppose you want to use anything in NumPy within the Python, so you have to say I'm going to use something within the box called NumPy. So that's what is called it's called importing the modules. So here I'm going to use the container which is having the linear algebra within NumPy. So which means I'm going to say it's NumPy.linear algebra. I'm going to import it into my namespace, and once I import it, I'm going to use this function called solve. So this solve function basically, if you give it two matrices, it will give you what the solution is. So the solution can be obtained just by writing x equals numpy dot linear algebra, and solve is written within linear algebra. So numpy is a box inside which linear algebra is another box, and inside which solve is one particular object inside the two boxes. So that's the final destination I'm going to look at. So it's numpy dot linear algebra dot solve of the original matrix you kind of started with. So it's A original and B original. So you can see the solution comes out to be exactly the same you determined using your handwritten code. So the solution is 1, minus 2 and 3. And again here I'm using the similar thing in SciPy. So SciPy also has the linear algebra module, and it also has the solve function. So you get the same solution both from the NumPy and from the SciPy, this particular function called solve. John, is there any questions I can take at this moment? Because I know this is kind of pretty abstract today.
Yeah.
If there is any questions, I can take it at this particular point. Because after this, it's just going to be the same thing repeated, but for a different method.
Yeah. Investigator Ghana, do you have any questions to ask so far? Okay. I didn't hear you.
Please, we are okay.
Okay.
Okay. So, John, should I go ahead?
Yeah. I think so. Yeah.
Yeah. Okay. Okay. So now I'm going to use another method where I'm going to use a mixture of techniques from both NumPy and SciPy to solve this problem. So all of you must have done this particular thing where you take a matrix and you can decompose it into two matrices, one which has a lower diagonal form and another which has the upper diagonal form. So depending upon the constraints you put on L and U, which basically is given here, they have different names. The Doolittles, the Krauts, the Choleskis, and all these things are there. And all I suggest is you need not kind of try coding up all these things, because this particular methods are really becomes really complicated and cumbersome to code. So you can have all these things written up in one of these numerical methods in Python. So let's take this equation where I have this method. So earlier I took A, I convert it into either L or U. So now what I do is, there are some matrices which cannot be converted into L and U directly, but they can be converted into L and U separately. So what we do here is, I take A and I get two matrices which are L and U. And now what I do, I say Ly equals B. So which means the Ux can be recast into another vector which is Y, and you have Ly equals B. So once you have this form, now you know how to solve it. You know you have to use the solve function to get Y. So once you get Y, then you have this another equation which is Ux equal to B. This particular step which is Ux equal to Y, and from here you can again use the solve function to get X equal to Y U inverse Y, and you get X by backward substitution. So now let me go into the algorithm part. This is a flowchart of what I should do. So first thing is, NumPy doesn't have any method to give you LU decompositions. So they have only certain other decompositions which can be done. So what I do here is, I read the matrix A, I read the matrix B, and then I use this particular function which says L comma U is SciPy.linearalgebra.lu of A, which is I pass matrix A and ask it to return L and U. So these are the two matrices which will be returned by the module, which will be returned by this particular function which is called LU. This function LU. Sorry. So once you get this, then I'm saying y is nothing but the dot product of u comma x, which is I'm performing this operation. U into x gives me y. So once I have that, now I'm going to ask the question, I'm going to solve this particular step, which I haven't mentioned here. So I'm going to solve by saying y equals numpy dot linear algebra dot solve of b comma y comma l. And then finally I'll get x equals the same way, and you will finally have, you can print the value of x. So let's look at what is there in the code. Okay, I think I didn't paste the snippets of the code, but this code has just only 4 lines, okay, which exactly does what I told you here. It first takes a and gets lu, and then it gets multiplies u and x to get you y, and it solves for y, and finally it solves for x. So it's just basically 4 lines of code in addition to the part where you read the matrices. So this is basically the output which we have after we do all those operations. So matrix A is read in 3 by 3, matrix B is read in which has a dimension of 3 by 1, and finally the first part where you get the L and U, this is after getting L and U. So you will get, this is your L and this is your U. And finally after solving this, you will get the same solution, which is again 1, minus 2 and 3, which is same as what we determined using all the other techniques which have been discussed before. Okay, so this brings me to the end of my lecture, and all I want to do is, there are a lot of other important tools. This is only within the linear algebra, but remember NumPy itself or SciPy itself is a huge tool set. Okay, all I had discussed today is just only about the linear algebra, and I agree, I guarantee you that your programming will be very easy, and you will find it to be a lot of fun once you start doing it. So today what I presented, if you're not really well versed with Python, you may not appreciate what is what is so great about this. But only if you start doing the programming and you start to feel for yourself, you'll know how awesome this particular thing becomes. You have a lot of things which you can do even without doing any sophisticated calculations. So sophisticated calculations need not be there for people who really don't need it. Okay, all you need is the solutions. So you have to go through these websites and find out what method you want. Just spend some time, and you can find that all these things are described in this manuals. There are 2 manuals which you can download for free. So one is the manual for NumPy, another is the manual for SciPy, where they exactly tell you what you should do along with examples. For example, if you're trying to do something which you, so John, is it over?
Let me see. You did you have a question or?
No question yet, please.
Okay. And remember, you had to, this is some of these things comes to default with Python, or otherwise it's just a very simple installation. You just need to follow the instructions which is given on the website. So if there are no questions, then probably, I will leave the presentation and I will leave the codes with you, and good luck with your programming thing.
Thank you.
Thanks, John.
Okay. Yeah, so I guess since it's an introductory lecture to Python and applications to numerical methods, I guess probably for a subsequent lecture we can build upon that and do more advanced applications once they play with this for quite a while.
Yeah, I think first because I'm not really sure about what is the level at which they know the programming thing. Anyway, I assume that they know, as you told me, I assume that they know at least the basic programming things in Python.
Yeah, they do. So I guess with this, yeah. So once they play with this, and then I guess for something subsequent, it will be maybe some more sophisticated applications that would be interesting for them. But,
Yeah, that'll be great.
Yeah. Okay then. Margaret, do you have any questions or comments to make? Or
No, please.
Okay.
Yeah, fine.
Okay.
I think I finished in time, John.
Yeah, that's yeah. Okay then.